Hello, welcome to lesson 6, the final lesson from chapter 7, trigonometry and modelling. And we're going to model some real life situations now using the harmonic trig functions. Harmonic in the sense that we start off with harmonic functions, but then we rewrite them using our compound angle formulae, okay, such as r sine and r cos in that form. So once again, usual prerequisites in the preparation, and please pause the video and have a go at the 4 warm-up questions. Okay, and let's have a look at the answers. Okay, so first up we have a conversion to do. We haven't done one of these for a while, probably not since GCSE in fact. And you're given the information, which you probably knew already, that 1 hour is of course 60 minutes, which is going to be useful. And we're going to convert 0.38 hours into minutes. So if we just set up the direct proportion, I'm just going to write it out. So 1 hour is equal to 60 minutes. And then obviously we can manipulate each side of that equation, if you like, that proportion, and we can work out whatever hours and minutes we like from that information. So we need 0.38. So the obvious thing to do is let's multiply both sides by 0.38. Okay, like this. And we'll see what we get. So obviously that will give us the 0.38 hours that we need to answer the question. Multiply that by 1. This is also referred to as the unitary method. You may remember from GCSE and before that, when you're comparing an amount to 1, okay, which you see in ratios. And then if we do 60 multiplied by 0.38, so if I do that on my calculator, 60 multiplied by 0.38, what do we get? So let's put it as a decimal. That's going to be 22.8 minutes. All right, so we'll write that in. So it's 22.8 minutes. Now, this is where you don't get too excited, and I've just realized I forgot to put the multiplication sign on, so it looks a bit odd. We have to give our answer to the nearest minute. So this is approximately equal to, if we round it to the nearest minute, would be 23 minutes. Okay, so that's the answer to that one. In question 2, we're going to use our result from question 1, the result being that 0.38 hours is, of course, 23 minutes to the nearest minute. And we're going to write down the time of day, 5.38 hours after 22:30 in the 24-hour clock. So that would be 10:30 p.m. So 5.38 hours, let's just write down what that actually means. This is in hours, of course. Now, we would need... If we're using hours and minutes on a 24-hour clock, we probably need to have 5.38 hours in hours and minutes also. So this would equal 5 hours. And the 0.38, of course. So remember, this is, of course, it's 5 plus the 0.38, which we've just figured out. So it would be 5 hours and approximately 22.8 minutes. Okay, but because this is all digital, it's on like a digital clock face, we'll leave this as 23. So that'd be 23 minutes. All right, so I hope that makes sense using our previous result. And we have to add this time on to 22:30. Well, if you add 5 hours to 22, then obviously that's going to be 27, but we don't have 27. So this is going to take us to 3 in the morning, isn't it? So it's 3 a.m. And then if we add the 23 minutes to the 30, in fact, I'll just write it down and then we'll convert it into the 24-hour clock in a moment. So I'm going to be adding on the left-hand side, I'm going to be adding 5 hours. Okay, and this is linked to a bit of group theory. So if you're doing maths at uni, you'll be doing a clock arithmetic or modular arithmetic, which is quite interesting. And then if we add 23 minutes on the minutes column, like that, then what do we get? Well, we get the 27. I'll convert that in a second, which obviously doesn't make sense at the moment, but we get also 53 minutes. But we don't have obviously 27 hours in a day. We only have 24. So this would be 3:53 a.m. Okay, or 3:53 on the 24-hour clock display. Okay, now for question 3, this is the third of our series of unusual questions, I think. We're given two functions, f and g, and they're plotted on the grid that you can see there. And you're asked to make a single change to f of x or g of x. So just a single change, and it can be to either function, to make it into a single continuous graph. Well, if you notice, the functions are defined for very limited domains. So f is only defined between 0 and 2, as you can see here, inclusive. All right, and then you can see how this just produced a short line. Okay, it's not an infinite line like you would get for fx equals 2x plus 1 when x is all real numbers. And also we've got a restricted domain of 2 to 5. And to make it a single continuous graph, well, one of the things you can do is, I'm just going to add this to the diagram. I could basically take my f of x, and if I could drop it down by 1 unit, so in other words, perform a transformation in the y direction by 1 unit, then I would create what we call a piecewise continuous function, because what you would get is you would get a straight line with the same gradient, of course, of 2, which would join up. And I'll just get rid of that arrow. It's just blocking the view. Which would join up to the function g, and the whole thing is defined as a piecewise continuous function. So that's one thing you can do. And in order to do that algebraically, of course, if you're going to perform a translation, which is what it is in the y direction, and you want to move 1 unit down, you're translating by this vector. So you'll be translating by the vector 0, okay, because obviously it's not going to move in the x direction at all, and then minus 1 in the y direction, which basically just removes 1 from the function. So the f of x, this is one possible idea. You could change the f of x by changing the value of c, essentially. So if you just had f of x equals 2x and drop the plus 1, you could do it the opposite way. You could take the g of x and you could add 1 in the y direction by using this vector on g. So this is another possibility, and there'll be other possibilities as well, but you could add 1 to g if you wanted. So 0.3x plus 4. They're just 2 suggestions there that might work. Okay, and moving on to question 4, we have a bit of revision of the harmonic trig function stuff that we've done recently in this chapter. So we have a linear combination of sines and cosines with coefficients 0.7 and 2.4. And what we're asked to do is just to find the value of r. So we're not asked for the alpha and the full thing, just the value of r. And you can use the identities and write out the whole thing. You can multiply the whole identity by r. You can equate coefficients. But the simplest way to do it, which is what we saw as a consequence of all that, is to just look at these coefficients here and apply Pythagoras' theorem on them. And it doesn't even matter if there's any negative values in there. The Pythagoras theorem calculation we'll sort that out. So r squared is simply going to be 0.7 squared plus negative 2.4 squared. And it's up to you if you want to include that negative or not. It makes no difference. And if we do that, so we're going to get 0.49 plus 5.76. And you might also have noticed in maybe calculating this, or you might have noticed this beforehand, that these are rather special numbers, aren't they? So if you add those together, you of course get 6.25, which looks a bit like a square number that we're familiar with, doesn't it? So this is r squared. So therefore r is just going to be the square root of 6.25, which is of course 2.5. Okay, so this is a slight adaptation of a Pythagorean triple. So the triple that we're looking at here, I just draw it for you, is of course it's going to be 7, 24. Obviously, this is not to scale, and 25. So that's a famous Pythagorean triple. And the great thing about the triples is there's an infinite variety of them. You can, as long as you scale them up in the same way, they still work. So in this instance, we've divided all the sides by 10. So we've made the proportion 1/10 of what it was, and it still works. So yeah. So just a bit of revision on what we did earlier in this chapter. Okay, so in worked example 1, we have a real life scenario involving cabin pressure in an aeroplane at cruising altitude. So there's quite a lot of information for us to take in initially. The first thing to notice is the cabin pressure P, denoted here, is in pounds per square inch. So you might not be familiar with that. Pounds per square inch is an imperial measurement of pressure, force over area. And we've got this aeroplane at cruising altitude. Okay, so there we go. We'll just highlight that, might be important. And this cabin pressure at cruising altitude is modeled using this equation. Okay, and we can see it's a trigonometric function. So there is some kind of fluctuation or oscillation in the pressure. And you can also see that this pressure is dependent on time as a variable here. So it's a function of time, the pressure. What that means is that the pressure will vary as time moves forward. Right, okay, so what do we have to do here? Well, we have to state the maximum and minimum cabin pressures. So if I just write out the equation that we've been given, so I'll put it here. So we've got A, and the pressure is 11.5, subtract 0.5, multiplied by the sine of T subtract 2. Okay. Now then, we have to consider what would happen at the minimum and maximum values of this function. So we know they exist because we have to state them. And the fact that we have to state it, as it says here, means that this should be relatively straightforward. And it all hinges on the sine function. Okay, now you might be familiar with where we're going with this. The sine function, as we know, has maximum and minimum values. So I can confidently state that it doesn't matter what is within the bracket here, because that is obviously going to be a transformation in the horizontal direction of the t variable. So that doesn't matter. So I can confidently claim that the range of, let's say, sine of t subtract 2 is just going to be this. There is no way that the sine of t subtract 2 can be anything other than values between and including -1 and 1, because that is a key property of the sine function. Okay, so those are the maxima and minima of the sine function. So how does this play out in our question? Well, the easiest thing to do is just take these values that we've just figured out, okay, the -1 and the 1 here, and we'll sub them into our p function. Okay, so I'm going to basically replace the sine function here. Because I know I've got a maximum and a minimum, if I replace that sine function with both of these two values, I should generate a maximum minimum value of p. Now, this is what we've got to be careful with this, and you'll see why in a second if you've not spotted already. So rather than saying I'm going to find the maximum and the minimum in that order, I'm just going to write p here. I'm just going to leave a little space, and we'll come back to this in a second. All right, and I'm going to sub in -1 first of all. So we're going to have 11.5 subtract 0.5, and I'm going to substitute in the minimum value of sine of t subtract 2. So I'll sub that in, so that's -1. Okay, so I'll make that really clear in red. Now then, you'll notice we have a double negative, don't we? We have the -0.5 here multiplied by the -1. So that's going to become a positive, which means we're going to be adding 0.5 to the 11.5. So this is simply going to be 12. Okay, once you figure that out. And excuse me, the next value we sub in is obviously going to be 1. So that's going to be 11.5 subtract 0.5 multiplied by this time 1. All right, and if we plug that in, that's going to be 11.5 subtract 0.5, which is just 11. Now, this might have been counterintuitive, but it's because we are subtracting the sine function from 11.5. Now, you'll notice that when we sub in the -1 here, this generates the maximum value, and when we substitute in 1, that generates the minimum value. So we can call this one P max, and we'll call this one P min. So I wanted to be careful with that because of the fact that the sine function is subtracted from that constant 11.5. So it's always a good idea to take great care when you're subbing in the maximum and minimum value of sine or cos or whatever it is, because you could make a crucial mistake there. So that's part A done. Now then, for part B, it says find the time after reaching cruising altitude. So that means this P function is in play, that the cabin first reaches a maximum pressure. Well, we know it reaches a maximum pressure when the sine function is at a minimum. Yes? So let's just draw that out for part B. So we'll do that. We'll have part B here. So maximum pressure, as we've just found, means that the sine of t subtract 2, remember what we had when we had the maximum pressure? I'm just going to draw your attention to it again. There it is. It was when we subbed in -1, wasn't it, for sine of t minus 2. So that's when we get the maximum pressure. And if you wanted to, you could just set the whole P equation equal to 12, rearrange it, and you'll quickly get to this step that I've just written down. Okay, so that's a really important fact. Okay, so we're going to be solving this equation here. And remember, of course, t is time. And time, obviously, if you're measuring something in a function, your time is going to be greater than or equal to 0 unless specified otherwise. Okay, so let's solve the equation. So at the moment, and this is going to be in radians, isn't it? I think. Does it say in the question? Yes, angle measured in radians. Yes, it is. Just there we go. It's really important. So let's find the principal angle. So principal angle time. Okay, and if you want to, you might just want to rewrite the function as sine of big X equals -1. Okay, just to make sure. If you're not comfortable with t subtract 2 directly, you can do it like that. So the principal angle X is going to be the inverse sine of 1. Remember, when you're finding the principal angle, you ignore the negative sign. Okay, that's really important. That negative sign is ignored, and I think it'd be worth just to make a note of that. So ignore the negative sign. Remember, because the cast diagram deals with the negative sign for you, okay, which we're going to use in a second. Okay, so that's what X is. It's the inverse sine of 1. So I'll carry on in green. And that's going to give us pi over 2. Okay, 90 degrees in other words. Right, so that's our principal angle. Now, for our principal angle, we have to find the time after reaching cruising altitude that the cabin first reaches maximum pressure, the first occasion. Now, remember, of course, if you have a principal angle and you're sticking it on a cast diagram, as we're going to do now, there are an infinite possibility of answers if we don't if we don't restrict our domain. So we're going to have to be careful here as to how many times we go around and what actually would be the first instance. Okay, but you'll see how it works in a second. So let's put our cast diagram on here, like so. C, A, S, and T. Okay, and remember, of course, that we had a -1 here. So we need to put our pi over 2 in the negative quadrant. Okay, this pi over 2 that we just figured out, the principal angle. And of course, sine is negative in C and T. And you'll notice very quickly, if you put pi over 2 in, you're just going to get one answer, which is going to be along here. Okay. If you want to cheat, of course, you can put an acute angle as pi over 2 and then just show that obviously this would just give the same value, but it's completely up to you. So this is pi over 2. All right, going that way. Okay, and going that way as well. And they meet. So we just got the one answer. So the question is, what is the first instance that the cabin pressure first reaches, so apologies, the time after reaching cruising altitude that the cabin first reaches the maximum pressure? Well, if we went sort of gung-ho into this and just wrote down the answers, so obviously we can say X is going to equal, well, if you start at 0, of course, and go in the positive direction like this, your first instance is obviously going to be 3 pi over 2, because you've got pi here plus pi over 2, which is 3 pi over 2. So I'll put that in, but you'll see what happens in a second. If I put 3 pi over 2 in as a possible answer, that's probably going to be the first one, if just looking plainly at the cast diagram. But remember, of course, that the X value here is t subtract 2, isn't it? Okay. And if you put pi over 2 on your calculator, into your calculator, you'll see that it's a value less than 2. So what that means is that we could actually even go in the negative direction this way and take negative pi over 2 as a possible answer. Okay, which is why I left a space. And you'll see why now. So that means that t subtract 2 will be equal to either negative pi over 2 or 3 pi over 2. Okay? And if we add 2 to both of those, it's absolutely crystal clear that your first t value is going to be 2 subtract pi over 2. Okay? We don't need the other one because it's the first instance when it first reaches a maximum. Okay? So that answer that I've just written down is the one we want. That's the first instance. And you've got to think ahead. You've got to plan ahead. This is problem solving. If you'd have gone straight into it and wrote 3 pi over 2 as the first answer, you would have missed the first instance. You would have got the second instance, but not the first instance. So let's just write down the answer as a decimal now. So just do that in different color. So in other words, just trying to fit it all on one page. This is going to be 0.43, I think. .43, and the time is in hours. So there we go. Now then, what you might be asked to do as well is to give the time in minutes, perhaps, as a more sensible answer. I mean, we could do that up here if you want. So if we have 0.43 hours, okay, just multiply by 60. And you'll get the answer in minutes. So if you do that, that's going to be, I think that answer is going to be 26 minutes. As a more reasonable way of writing the answer. So there we go. So after 26 minutes, the cabin pressure first reaches its maximum. Okay, so that concludes part B. Okay, so moving on to part C, we have to find or calculate the cabin pressure after 5 hours at cruising altitude. So this is a little bit more straightforward than the previous part, which is unusual. It usually builds up, doesn't it, as you're working through a question in terms of difficulty. So all we have to do really is substitute in t equals 5, okay, for the 5 hours into our function for p. So p is simply going to be 11.5. Obviously, check that the units are correct. It's 5 hours, and time is measured in hours according to the model. So sine of, and we'll sub in t is 5, so that's 5. Subtract 2. There we go, and that's substituted in. Just tidy up a little bit. So that's 11.5. Subtract 0.5. Multiplied by the sine of 3. Now, remember, this is in radians. Okay, so we'll use our calculator for this. Just bring the calculator up. Make sure your calculator is set to radians, as I have here. Okay, just use the angle input on setup if you haven't done that already. And let's type it in. So we're going to have 11.5. Do it all in one go. Subtract 0.5 multiplied by the sine of 3, and then close your bracket. Okay, and that will give us 11.4. Now we just have to check now, do we have to give this answer to any particular accuracy? If the answer is no, then we'll round to 3 significant figures, which is the standard way of doing this if it was an exam situation. So 3 significant figures unless specified otherwise. So that's going to be 11.4 psi to 3 significant figures. Okay, so that's part C done. Okay, just make sure you indicate that that is rounded. And also for part D, we have to find all the times during the first 8 hours of cruising that the cabin pressure, I'm just going to have to move the calculator so we can see that the cabin pressure would be exactly 11.3 psi. So it doesn't look like there's that much fluctuation, okay, in this. So let's see. First 8 hours. Well, if it's the first 8 hours, of course, that means that we only have to worry about t being between 0, will include 0, of course, and 8. So that's the first 8 hours. And we want the pressure to be exactly 11.3. Okay, so we set our equation equal to 11.3 and see what happens. So let's write it out. So we have 11.5 subtract 0.5 multiplied by the sine of t subtract 2. And when is that equal to? 11.3, which is given to us in the question. Okay, well, one thing we can do now is we can subtract the 11.5, the constant, from both sides. So let's do that as our second step. It's completely up to you how you do this. This just seems like a sensible second step. So we've still got the negative 0.5 sine of t subtract 2. And if I subtract 11.5 from both sides, of course, that's going to give me a negative value, which is negative 0.2. Yeah? Okay. Now we have a double negative, as in we have negatives on both sides. So they will cancel. So in other words, I can just divide both sides by 0.5 and remove the negative. So we're going to have a situation where we have sine of t subtract 2 equal to, and I'll put this step in because this is important, so that's going to be 0.2 divided by 0.5. Now, you'll notice that will simplify to 2/5, or, if you prefer, 0.4. Okay, so this is the equation we're going to have to solve. So I'll move up to the other side so we have a bit more space. So moving up to here. Now I'll use the letter y this time. So let big Y equal t subtract 2. Although I suppose I don't have to, but just to make it distinct from the previous part. Okay, so therefore we have sine of big Y is equal to 0.4. Okay, nice and positive. We have our substitution. Let's find our principal angle. Principal angle. Okay, so we do the inverse sine of 0.4. Of course, this is all going to be in radians. All right, and we get our calculator. Okay, there we go. So we do the inverse sine, so shift sine and 0.4, plug that in. What do we get? Okay, all right, so we get this in radians. Now, of course, if you're not comfortable with radians, of course, you can change into degrees. When I say change, you can convert into degrees and then convert back again. But we've done these a few times. I think it will be okay to use radians now. So this is 0.4115. Okay, and it's a good idea. Let's use 4 decimal places for this. So let's write that down. So it's going to be 0.4. Let's get the writing tool on and just change that color so we can see it. 0.4115. And we'll just tell everybody that we've rounded that to 4 decimal places. It's not an exact answer, as you wouldn't expect. Okay. Now then, one thing we haven't done, of course, we haven't adjusted our interval. So we know, of course, that we're interested between t being between 0 and 8. So let's adjust the interval as well. It doesn't matter which order you do this, as long as you do it. So remember, I'll just write the interval that we wrote down earlier. So first 8 hours of flight would be that. So we have to subtract 2 from everything. So that's going to give us -2. And then, of course, we've got now t subtract 2. And subtract 2 from 8. So it's 6. So we're going to be looking between negative 2 radians and 6 radians for this. Okay. If you want to convert into degrees, you can do, if that makes it more comfortable. Right. Okay. Ready for the cast diagram now, and we can get all our answers. So I'll get the cast diagram on here. C, A, S, and T. Okay. And just to give you a bit of an idea, obviously 0.4 is going to be a nice acute angle. Okay. It has to be an acute angle because we did this on the calculator, and the calculator, if you're putting in a positive number, will return an acute angle. Remember, because all the sine trig, all the trig functions are all positive in that first quadrant. Okay, and they're all acute, of course. So at this instance, because we have 0.4 is a positive number, we use the 2 positive quadrants for sine. So we'll just add, add the angles on this. That's going to be 0.4115 there, and drawn it a bit lopsided, haven't I? 0.4115 in that quadrant. Those are in radians. Okay. Right, now this is the y variable, isn't it? So just to remind you, this t subtract 2, and I forgot to write that on, that's the y variable. Okay, so anything between negative 2 and 6 is fine. So let's start going around our cast diagram in that direction. Well, negative 2 would be over here. So when I say over here, you can't see where I'm pointing, but negative 2 radians, let me just give you an idea what that looks like, would be somewhere in the t quadrant here, somewhere around here. Okay, that would be negative 2. So we're not really interested in that. The first angle we're going to get to is the 0.4115. Okay, so we'll just go around and we'll get all the answers we possibly can. So first one will be 0.4115. Okay, and we have to go around all the way around to 6. So the next angle, and I'll use my calculator for this one, is going to be pi subtract the 0.4115. So we'll do that. So inverse that button there. So there's the pi button, subtract 0.4115. Okay, and we get 2.73 and loads of other stuff, which is about 2.73 actually, isn't it? That's going to be the next angle. Nope. 2.73, not 0.273. 2.73. I'll put 0.1 if we round it. 4 decimal places. Okay, so that's good. Now then, do we have to go around again? Well, let's just check. If you're not particularly au fait with radians yet, if we went round a full turn, of course, that would be 2 pi, wouldn't it? Now, 2 pi, we do that as decimals. If you haven't done this yet, is 6.28. Now, clearly that is more than what's required. Okay, so a full turn wouldn't be necessary in radians. So that means that we've got all possible answers here, all written down for us. Now then, let's figure out what our t values are going to be now. So remember, we're going to replace the y with t subtract 2, which we can do. So we're going to have t subtract 2 is equal to all the same stuff. So 0.4115 and 2.7301. So all we have to do to get our final times is to add 2 to those values. So therefore, t is going to be 2.4115. Don't need a calculator for this. Or 4.7301. Okay, now just before you get really excited and think, yes, I've done it, let's just check that we've got all the information correct. Right, let's just remove remove the calculator. So it says find all the times during the first 8 hours of cruising that the cabin pressure would be exactly 11.3 psi. Well, we've got two values, and these are in hours. Okay, but I think it might be better if we converted these to hours and minutes. All right, so we're going to go back up to the top left. So the first, let's convert to hours and minutes. Okay, now then, in order to do that, you just have to worry about the decimal parts and multiply that by 60. Essentially, we can keep the hours part as they are. I mean, we can see clearly that we've got 2 hours and 4 hours here. It's just what about the decimal part? So we'll do those as separate little calculations. Okay, so first of all, what is 0.4115 in minutes? Well, just multiply by 60. So let's get the calculator back up. We'll clear all that. 0.4115, multiply that by 60 is 24.69. So approximately 25 minutes. Let's get that written down. Use the proper function. So it's about, I'll put approximately, we're rounding, aren't we? We'll give it to the nearest minute. Okay, it doesn't specify, but just in case, and this might come up in an exam, and 0.7301, if we multiply that by 60, what is that going to be in minutes? Well, okay, we can do the same thing. So 0.7301, multiply that by 60. I've done that wrong, sorry. 0.7301 multiplied by 60. Okay, 43.8, so about 44 minutes. Okay, good. So it's about 44 minutes. And if you're not sure you've done that right, I mean, use your common sense. Okay, we know 3/4 of an hour is 45 minutes. That's just slightly less, isn't it? 0.73. 3/4 will be 0.75. So let's write down our final answers now. So you're going to have a time, we'll call it T1, is going to be 2 hours and 25 minutes. And the second time, we'll call that T2, is going to be 4 hours and 44 minutes, according to this model. And as mathematicians, of course, you would check these times against what really happens, and you can adjust your model accordingly. Okay, so that concludes the first example. So for example 2, this is a combination of several exam style questions which have been a regular feature for the last few years, even before the new specification started. So for this question, we're given some more familiar introduction here. We have a harmonic expression in terms of sine and cos of theta, and we have to use the identity or the expression given here, which obviously links to an identity, and we're given the usual restrictions on r and alpha. Okay, alpha being an acute angle, of course, and we have to calculate alpha to 4 decimal places. So that's the first part, and then we can see how this sort of more handle turning math, as I put it, where we just sort of follow the recipe. We'll see how that can apply to a real life model later on in the question. Okay, so for part A, I've written out the expression we've been given again, and we've set it identical to the sine identity. So the next job, of course, is we need to break open this sine identity, and then we can equate coefficients. So let's do that now. So this is all going to be identical to r, and then we'll use the big square brackets here, and then we'll put in the sine identity, which of course is in your formula booklet. So this is sine theta cos alpha subtract cos theta sine alpha, and we'll close those big square brackets. Next step, of course, is we're going to multiply through by r. So final steps, this is going to be r sine theta cos alpha subtract r cos theta sine alpha. So according to this concept, the expression on the left is identical to the expression on the right. So let's equate the coefficients now, because that's what we can do when we have identical expressions. So on the left-hand side, we have root 2 multiplying the sine theta. So that root 2, of course, must correspond to whatever's multiplying sine theta on the right, which is the r and the cos alpha. So that means I can now write down an equation. So we can now say that r cos alpha must equal root 2. Okay, and I will name that equation 1, which suggests we're going to be using simultaneous equations, doesn't it? Okay, so that's good. We'll apply the same rationale to the second term. So this time we have a negative on both the left and the right. So I can just ignore that really. I can just take the 3 root 5 and compare that to the r and the sine alpha. And I'll just explain that again. It's because we have the negative right there on the left and the negative on the right, so you don't need to worry about that. All right, so let's write down another equation. So we now can say that r sine alpha must be equal to 3 root 5. Okay, and we'll call this equation 2. In fact, I'm just going to change my square root. Didn't look much like a square root, did it? Let's try that again. That's better. And this is equation 2. And you'll look at those and think, okay, we've got 2 unknowns. We need to solve for alpha and for r. Let's divide them. So if I do equation 2 divided by equation 1 and compare the left and right hand sides, we will get r sine alpha divided by r cos alpha on the left hand side, of course, and that would be equal to 3 root 5 divided by the square root of 2. There's no need to rationalize it. That's not the point of this. It's to find out what alpha is. Okay, and then this is where the magic happens. Essentially, we've got the cancellation of r. Okay, there's no magic, of course. It's just mathematics, isn't it? Got the cancellation of r. They're non-zero, so there's no problem there. And then we have sine alpha over cos alpha, which, of course, as we all know, is tan alpha. So therefore, we now know that tan alpha is going to be equal to 3 root 5 divided by the square root of 2. Now, that means we can find alpha directly. Because alpha has that restriction on it, it's an acute angle between 0 and pi over 2. I can use the calculator and just write down what my calculator tells me, because the calculator will give me the acute angle always. So let's get the calculator out now. Make sure your calculator is set to radians. Let's do this. So I think I'll have to go back to the menu. Option 1. Yes, I'm in radians there. Okay, so we just have to do the inverse tan of 3 multiplied by the square root of 5. Just come out of that, and we can divide that by the square root of 2. Doesn't matter how you do it, of course. And let's see what we get. Okay, so we have to write this to 4 decimal places. So my solution is going to be 1.3630 radians to 4 decimal places. Okay, So that's good. So we've now got our alpha set up now, which will go into our identity momentarily. We also need to find R. Now to find R, of course, we can just apply Pythagoras' theorem to the coefficients on the left-hand side. So it's the √2 and the 3√5. We just assume they are the shorter sides of a right angle triangle. Okay, if you want an explanation for why that is, it's in a previous lesson. So let's do that. So R squared is simply going to be the √2 squared. All right, so √2 squared plus the 3√5 squared. So that's 3√5, and we'll square both of those. So good opportunity to practice your surds here. Now, obviously, √2 squared, the root and the squaring are inverse operations, inverse functions, sorry. So that's obviously going to give us 2. And we have to square the 3 and the √5. Well, if we square 3, we get 9. So 3 squared is, of course, 9. And 5, the √5 squared is, of course, just 5. So it's the product of 9 and 5, isn't it? Which is 45. And we add those together. So it's 2 plus 45. And I'll just put the answer here. So that means that R squared is 47. So in other words, R is going to be the square root of 47. Not a nice answer, but an answer nonetheless. Right, so we've got our two unknowns. We've got R and we've got alpha. Both not particularly nice numbers, but this is what happens when we're going to look at modeling situations, okay? So we're going to move on to the application side in a moment. And what we can do first, though, is we can write our expression, our harmonic expression, using R and alpha. So let's do that. So we've got, and I'll just remove the calculator so we've got a bit of space. So therefore, we now know that √2 sine theta subtract 3√5 cos theta is identical to all the stuff we've just found. So √47, all right, that's the R, multiplied by the sine of theta, subtract, and the value of alpha, which is 1.3630, and we'll close that bracket. All right, so that's really crucial, and because we've done this work, obviously it's going to play a part in the remainder of this question. All right, so what I've done, I've just come back up to the question and I've written down our result from part A, so we can see what we've discovered. And we now have this model. So this model represents the depth of the water at a harbour in Southview. And this is Alice's model. And what Alice did is she collected data over a 12-hour period. Okay, so that's important. So the data she's collected represents 12 hours of time. And she started collecting the data after midnight on the 15th of November 2018. So for a 12-hour period, that would be from midnight till 12 noon on that day. You can see this in the model because it's represented by the time t, okay, which is a 12-hour period. So that all checks out. And we're calling the depth of the water d in meters, and it's a function of time. Okay, so what can we do with this? Well, we're asked in part B to find the depth of the water at 12 noon on the 15th of November. Well, straight away when we read that, we've just indicated at 12 noon, this is the final hour or the final reading, perhaps, of Alice's model. So it's when obviously t is 12. So we can just make a note of that for part B. And what we can do is we could just substitute 12 into the expression, sorry, beg your pardon, into the model that they've given us, or we could use our new way of writing it using the identity that we did in part A. So let's use the latter, and we'll see how our solution to part A links with this model. So notice it looks quite different. Now we'll just have a look at the commonalities between the model and what we found in part A. So we've got the root 2 sine part. Okay, that checks out here. Okay, so we've got that. We've got the -3 root 5 cosine part. That also checks out. So the only difference between the model and what we had in part A on the left-hand side is the 13.1, which is added to it. So I'll highlight that as a difference. I'll do that in purple. So this is a key difference here. We've got an extra 13.1. And also we've got these pi t over 12. So this is how the model has converted a time into an angle. Okay. And you can do that by converting the angle into, converting the time into some measure in radians, which is what the model does. So we can see from the left-hand side, we're going to have to make a substitution. So we can see that the theta must equal the pi t over 12. All right. And apart from that, it's all the same. We've just got to add the 13.1 as well. So let's rewrite the model using our new expression on the right-hand side. And we know that all we have to do is add 13.1 to it and substitute pi t over 12 in for theta. So this is really good. So let's write down what the new model will look like. So it's going to be d of t is equal to 13.1. Now we're going to add root 47 multiplied by the sine of, now instead of theta, of course, we're going to make the substitution. So we're going to use pi t over 12. Okay, and then we have to subtract the 1.3630 radians. Okay, so this is identical to the model that was given to us in the question. So that's really good. And for part B, we're going to substitute t equals 12 into it, and then we can do part C and D later. Okay, so for part B, I've just written out our new expression again. I'm just going to change that a bit. Looks a bit odd. There we go. And we're going to substitute in t equals 12 because that's the time when the model suggests to do it. It's 12 noon, and remember the recordings start at midnight. So I hope that makes sense. So we're going to sub in 12 into this whole expression on the right. So d of 12, and obviously use your calculator for this, plus square root of 47 multiplied by the sine, and then if we plug in 12, so we'll do that. So it's pi multiplied by 12. Okay, and then that's divided by 12, so got some nice cancellation there. Subtract 1.3630. So yeah, as I just mentioned, that there is going to be a cancellation here, so that's going to simplify to just pi. And yeah, we'll just do this on the calculator and see what happens, see what we get. So we'll just cancel that. So subbing everything in, I could do this in one step. So that's 13.1. Add the square root of 47 just come out of that, multiplied by the sine, and I'm in radians, that's okay. I know the 12s cancel out, so I can just put in pi here. So let's shift the pi button and then subtract the 1.3630. And just double check that before you do anything. Make sure you plugged in the numbers correctly. Okay, and let's see what we get. So this is going to give us the depth of the water in meters. Okay, right. So we get 19.8. So it's like a familiar number, twice gravity. So 19.81. Okay, so we'll say that. And I'll give that to 2 decimal places. Okay, so that's the depth of the water at where the model ceases to be valid. It's the final value. All right, so let's see what we have to do next. All right, so for part C, we have to find the maximum depth of the water and the time of day at which it occurs, and we give our answers to the nearest minute for that time. And later I'll show you how all this stuff appears on a graph. We'll use GeoGebra for that. So for part C, so we need the maximum depth. Now, if we just this sounds like it's going to be complicated for the maximum depth, but I'm just going to write out the model again. So we know that we've got all these ingredients in our model, so it makes it look very complicated. Okay, so it's the sine of pi t over 12 subtract 1.3630. All right, so let's just think about what this is telling us from what we know about transformations. So for example, if we consider the sine part of the model, which is here, what do we know about sine functions? Well, we know an awful lot about sine functions, don't we? The complex part of this is simply telling us that there is some kind of transformation going on in the domain. Okay, so that part just tells us that there is some stretching, there's some translation in the domain. It tells us nothing about the range at all. So I can say with confidence the following piece of information. So we know that if I take the sine of pi t over 12 and subtract 1.3630, it could basically be anything in there. All right, it doesn't matter because only the t coordinates are affected. But I know everything about the range. I know that the sine function is always between 1 and -1. And the only way that can change is if there is some kind of vertical transformation going on. So if the sine function is multiplied by some constant, or there is something added to it. Now, we know that that is the case in our model because we have the 13.1 and the root 47. But we're not interested in that. We're just isolating the sine part for now. We're just interested in this bit. Okay, and I know that that bit has to be the values it takes are always between -1 and 1. So what is the maximum value that this sine function can take? Well, the maximum value is, of course, 1. Okay, so I can say very, very clearly with confidence that the maximum value of the depth, so we'll call it d max, of t is just going to equal 13.1 plus root 47 multiplied by 1. Okay. Now we've seen an instance where it's not, where you don't put 1 in, where it's -1, but that depends on whether there is a subtraction in this part, okay? Because that's an addition, I'm maximizing it, aren't I, by timesing it by 1. If I wanted to minimize it, I would multiply the root 47 by -1, and then you would be subtracting root 47. So I just have to figure out what this value actually is. Okay, so we'll get the calculator and we'll see what this gives us. So I take the 13.1 again, and then let's just add the root 47. Okay, and see what that gives us. Okay, so we get an answer of 19.96. I'll give it to 2 decimal places again. It's not specified, but so it's going to be 19.96 meters, and I'll just say that I've rounded it to 2 decimal places. I don't like using 3 significant figures when you have two digits or so values between in sort of 10s and 20s, because you'll lose a lot of accuracy. So I think that will do. So that's the maximum depth of the water, 19.96 meters. Now the twist, of course, is we have to find the time of day at which this occurs. Well, we can do a lot with this because we've basically set up the question. So let's just make a note. So to find T at D max, so to find the time when the depth is a maximum, what do we have to do? Well, all we have to do is solve the following equation. So we know that the maximum occurs when all of this, the sine function part, 1.3630 inside the bracket, when all that is equal to 1. Okay? We just have to solve that equation. You don't have, you could set the whole d of t equal to 19.96 and rearrange it, but you would just basically get the same thing, and you might not quite get 1 depending on how you've rounded it. So that's the equation we need to solve. So we can solve this equation quite simply. So let's remove the calculator. So I'm just going to use a substitution. So let's just partition the board. Okay, and we'll say let big X equal pi t over 12 subtract 1.3630. Okay, so now I've got an easier equation to solve. So all I have to do is solve the equation sine x equals 1. All right, which is much easier. So principal angle. So why do I need to use a principal angle? Well, you'll see. So we just do the inverse sine of 1. And you'll know this. When is sine a maximum? Well, when x, in this case, is equal to pi over 2. 90 degrees. Okay, if you don't believe me, check on your calculator. So that's the principal angle. Now, why can't we just say, okay, that's what x is. Let's solve that by putting that equal to pi t over 12 subtract 1.3630. Well, we've got to be cautious because there are numerous answers, and because of this rather strange sort of collection of transformations going on here, it could be a situation where you get more than one answer or more than one valid answer, and you have to whittle them down. Okay, so we know that there's infinite answers to these equations, but only one specific answer will do. So we have to make sure we've got the correct answer, and you'll see what I mean in a minute. Now, for this, let's just make an adjustment to the domain. So we know that t is valid between 0 and 12. Okay, so we need to adjust the domain. Now, if I multiply everything by pi t over 12, sorry, by pi over 12, I should say, nothing happens to 0. Okay, but what's nice about this is because it's pi t over 12, the 12 and the 12 will cancel, so we get pi. All right, so we're looking in the interval from 0 to pi, but then we also have to subtract the 1.3630. So this is the actual interval we need to work in, 3630, which is less than or equal to pi t over 12, subtract that, which is of course just x. Okay, and we're going to have pi subtract 1.3630. Okay, so that's the range we're going to look in. So let's draw a cast diagram now. I'll put the cast diagram here. It's got a bit of space. So it's a positive number, isn't it? So 1 is obviously a positive number. We need to use the positive quadrants for sine, which are of course here and here. And because it's pi over 2, we're just going to get one value. All right, so it's all going to lie on that line. And it's just going to be pi over 2. Okay, no matter which way you go, you're going to get the pi over 2. All right, so what are my possible answers? Well, if I'm only looking in the very short interval from negative 1.36, okay, up to pi subtract 1.3630, there is only going to be one answer, and it's going to be pi over 2. Okay, so just confirm that using the cast diagram. So we have x is equal to pi over 2. So we just have to solve the equation now. So therefore, pi t over 12 subtract 1.3630 must equal pi over 2. Great. Okay, and we just rearrange. So we add 1.3630 to both sides, multiply by 12 and divide by pi. So I will do that on the calculator. All right, so let's put everything in. So we have pi over 2. Okay, there it is. All right, now we add the 1.3630. You can do this in more than one step if you want to. Okay, and that will give us pi t over 12. So we now need to multiply by 12 and divide by pi. So multiply by 12 equals, and then divide by pi. Use the pi button again. And we get 11.206. Now, let's write that in. So this is going to be 11.20. I'm going to do this to 4 decimal place again, 2063. Okay, and that's hours. Now, and that's the first instance that it happens. Okay, and the only instance, and we know this is correct because this is within the range. Remember, of course, that t has to be between 0 and 12, as we can see there, and clearly we are in that range, and it looks like it's very close to the end of the cycle, isn't it? So it's the end of the 12-hour period when this maximum occurs. Now, we haven't finished the question yet because we need to convert this into hours and minutes. So one way we could do that is, firstly, we could, on the calculator, which would be quite easy to do, if we just subtract the hours part. Okay, so I'm going to take off 11, so we just have a decimal between 0 and 1. So that's the fraction of an hour on top of the 11 hours. So how do we convert that into minutes? Well, we can multiply by 60. Okay. Okay, so it wants it to the nearest minute. So that's 12 minutes to the nearest minute, isn't it? So we can now just write down our answer in hours and minutes now. So it's 11 hours and 12 minutes. And if you have to put this using the 24-hour clock, of course, if we're starting at 11, sorry, I beg your pardon, if you're starting at 12 midnight, which is of course 0, 11 hours, 12 minutes is just going to be the time 11:12 on the on the 15th of November when this happened. So that's the answer for part C. All right, and for part D, we have to calculate the time to the nearest minute when the depth of the water is 14 meters, okay? And that time to the nearest minute again. So I'll assume that means the time of day, all right, based on the fact that the model starts at midnight. So let's set this up down below. All right, so I've just set this up. We've got an equation to solve where the model dt is equal to 14. So that's what we've got here. So I've just stated it first up. All that nasty looking stuff on the left equals 14. Then I've gone back to the substitution that we used previously, where we said x is equal to all this, big X. It's a function of t. I've rewritten the equation in terms of x now. And I've also used the interval that we discovered earlier, where x is between negative 1.36 and pi subtract negative 1.36. So we just have to solve an equation again. And you're probably thinking that this is a really, really long question. Well, what I've done is I've put together all the different things that I know they've asked in the past into one example, so we don't have to do multiple examples going through the same steps over and over again. So you get a full flavor of what could be asked of you. Right, so we can now solve the equation here. All right, so we just have to rearrange this. And first thing to do is obviously we're going to subtract the 13.1 from both sides and then divide by root 47. So solving this, we are going to get the square root of 47 multiplied by the sine of big X is going to equal 0.9. So that's 14 subtract 13.1. And then sine X is going to be 0.9 divided by that. Again, no need to rationalize it. We're just going to put it into the calculator. Okay. And that's a nice positive number. So we can now find our principal angle. And we'll use a cast diagram again. So principal angle all right, so principal angle big X is going to be the inverse sine of what we've just discovered. So that'll be 0.9 over the square root of 47. And we'll close those brackets. So we'll see what this is now. So let's plug all this into our calculator. Let's move the calculator over. It's got a bit more space. So we'll cancel that. So we do the inverse, the sine, okay, 0.9, divide that by the square root of 47, just come out of that and close the bracket. And, okay, so we get quite a small angle, don't we? So that's 0.1317 to 4 decimal places. That's, of course, in radians. So we have a small positive acute angle. So we can now add this to the cast diagram, okay? Make sure that there aren't multiple answers to this, okay? Although it is probably hinted in the question how many answers there are, whether it uses the plural or not. Just get rid of that. We'll get the cast diagram going. Okay. You've done these so many times. You can see as we're learning more, we're just adding layers and layers onto what we already know, which is one of the, maybe a good thing, maybe a bad thing, I don't know. So put sine in the positive quadrant. So that's A and C, and it's an acute angle, very small angle. So let's draw that on. 0.1317 and 0.1317 there. This is in radians. Now then, let's just consider the range. So the X angle is, it's going from negative 1.3630. So that's sort of somewhere down here. All right, and then if we're going anti-clockwise in the positive direction, and it will stop at pi subtract that, which is obviously it's 180 degrees, isn't it? That range, which will be somewhere there. So that means that the only valid region is all this over here. Okay, that's where it's valid. So we have one answer, which is valid, which is of course this one. Okay, so there's our answer. So we're going to use this and set this equal to X. So we have X is equal to 0.1317. All right, and then we just substitute the pi t, etc. back into this. So pi t over 12 subtract 1.3630 must equal 0.1317. All right, so we substitute. So we go back to our calculator now and we solve for t. So when we do that, okay, I'll do this for you. You will get 5. You can just check this on your calculator. 7092 to 4 decimal places. Now, again, we've got to make sure we've read the question carefully. It wants the time, presumably of the day, to the nearest minute. Well, if we convert this into hours and minutes, you can just basically subtract the 5. Okay, so you get 0.7092 and multiply the 0.7092 by 60 as we did previously. And you'll find that you will get 5 hours. And common sense will tell you just shy of 3/4 of an hour. So it's actually 43 minutes. That's to the nearest minute. To the nearest minute, okay. And then to give that in the time of day, measuring from midnight, of course, this is going to just be 43. So quite early in the morning. So that's the answer to part D, which is good. So we've got 2 times. We've solved 2 equations there. So let's see what we have to do next. All right, so for the final part of this question, we're going to take a look at Bob's model. Now, on face value, it looks almost the same, doesn't it? He's calling the height of the water H. Okay, so it's just another way of saying the depth of the water, how deep the water is. It's the height from the bottom. So he's calling it H meters. Okay, and H is a function of X. So what is X? Well, it looks as though X is basically the same variable t. Okay, it's the measure of time over a 12-hour period, and you can see that from the range of values of X, the domain. Okay, now so it looks like, apart from calling it H and substituting in X for t, we've got the same model, but closer inspection will reveal that this is not the same model. Okay, and it's all down to the detail in the question. So if we start from this point here, it says that Bob models the height of the water H meters at Southview Harbour. It's the same location over a 12-hour period. So the same so far, 12-hour period from 12 noon, okay, on the 15th of November. So Bob's model picks up where Alice's model left off. So his 0 hours here represents 12 noon on the 15th of November, meaning that the 12 would be midnight on the 16th of November. Okay, so that's really important. So this is on the 15th of November. Okay, and then this would be the 16th of November. So it's the next 12-hour period. Notice, of course, as well, that the value for 0 here is included. All right, so it's valid according to this for 12 noon. All right, and that's really important. Same as Alice's model. Alice's model is also valid for 12 noon, but that's when her t equals 12. So what is going on here? Well, it's probably best to show you using GeoGebra, because you can see the functions in front of you and see how they're behaving. So if I just show you, just clear what we've got there. We've got the two functions. Now, the blue one, this is Alice's model. I'm just going to label it. So this is Alice's. Okay. And the red one is Bob's. So we've got Alice and Bob. Okay. So they're exactly the same shape because they are the same expression in the function, aren't they? You know, you've got the 13.1 added to the root 2, beg your pardon, the root 47 sign and all the rest of it. It's the same model. So what do we need to do with this? So we've plotted both models. Well, you can see, of course, that Alice's model begins when t is 0. So this is the t variable here, but this t variable also coincides with the x variable. Okay, so if we just talk about this in terms of the same variable, as in t and x being the same thing, but measured across a whole 24-hour period, the x variable doesn't kick in until at the time t equals 12. Okay, so on Bob's model, this would be when x is equals to 0. All right, so you could argue that when t equals 12, x equals 0. So they're translated by 12 hours, essentially. Okay, if you want to think of it like that. Now then, so what is the problem with Bob's model? Well, Bob is measuring, or he's modeling the same thing that Alice is measuring. But remember, Alice has collected data for hers. Okay, Alice was collecting data between midnight and 12 noon. So between this time here and this time here, Alice was collecting data. So she might have plotted this model based on having lots of like data points like this, perhaps, and she's got a reasonably good model of the depth of the water. Bob hasn't done that. Bob has just taken her model and translated it by 12 hours. And if Bob was supposed to be measuring the same thing, then we know from this diagram that Bob's model should start where Alice's model left off by doing something like this. Okay, but it clearly doesn't, because he's been a bit careless in interpreting what Alice has done. So the problem with the model is the fact that there is a discontinuity between when t equals 12 on Alice's model and when x equals 0 on Bob's model. So that's why the question is asking you to consider the both models at the 12 noon time. So if we go back to the notes, let's just go through this last part of the question again. So it says, considering the depth of water at 12 noon on the 15th of November. Okay, so we'll just state what's going on at those times. So for part E, at 12 noon on the 15th of November, what do we know? Well, we know, according to Alice's model, the time is 12, and Bob's model, x equals 0. So we'll just indicate which model this is. So this is Alice, and this is Bob. Now, if the models are correct or if they're predictive, then the values we get when we substitute those particular values in should coincide. Now, we've already done the value of D when T is 12. So we know that D of 12, because we've already figured it out earlier, was 19.81. Okay, meters. Okay, and that was to 2 decimal places. So within a range of error, we should expect that H of 0 in Bob's model should also be that. Okay. Now, if we do H of 0, now depends how you want to substitute it in. We could just use the new way of writing the model, but it's not necessary really. We can use the model as it's presented here, just for a change, I suppose. So we put 0 into this, and what do we get? Well, let's try it. So you're going to get 13.1 plus root 47. Okay. Beg your pardon, I'm using this form, aren't I? Plus root 2. You can use the other version if you want to. Multiplied by the sine. Now, if I put 0 into this, it's going to be the sine of 0. So that's the sine of 0. And then I'm going to be subtracting 3 root 5 multiplied by the cosine of 0. Okay. And we know from long experience now that the sine of 0 is, of course, 0. I'll just put that in. So that's just 0, isn't it? Okay. And the cosine of 0, because of the translation of 90 degrees, that's the only difference between those two functions. One is a translation of the other by 90 degrees, or pi over 2. This is, of course, 1. Okay, so to get H of 0, it's simply going to be 13.1. Now, the root 2 multiplying 0 is, of course, 0, so I'm just going to be subtracting 3 root 5 from that. And we can see that they are not going to be the same, but we'll just work it out anyway. And we've seen that from the diagram. So if I take 13.1, subtract 3 multiplied by the square root of 5, just come out of that. What do we get? Well, we get 6.39. Okay, so this is equal to 6.39 meters to, let's write that again, to 2 decimal places. Right, now this is the conclusion that we can draw from this. And this goes back to that third question in the starter. So we now know from the two results we've got here, so the fact that the 6.39 is nothing like the 19.81, even though they're at exactly the same time of day. That's the problem. It's the same harbor, the same location, the same measurement at the same time of day, but we've got two completely different answers. That D of 12 is not equal or nowhere near equal to H of 0. So there is a discontinuity between Alice's model and Bob's. So that's just established that one of them is wrong. Okay, now if we look at the information in the question again, so if you just go back up to the stuff that's provided to us, if we just read through it, it says Alice's model is supported by measurements. Okay, measurements of D taken at regular intervals, as we indicated using the GeoGebra. Bob hasn't done that. He's attempting to use a similar model for the depth of the water, but he hasn't taken any measurements. So we know that Bob's must be wrong, because Alice has collected data to support her model, and Bob has just used pure assumption. So therefore, Bob's model is not correct. Now, if this is real life, of course, and you have discrepancies like this is where, as a mathematician, you would go back to the drawing board. You would have to collect data, and your model should fit real life as much as possible. And if it doesn't, then you have to go back and amend it. All right, so that concludes that worked example, which is very similar to the kind of thing you may get in the exam. That concludes the lesson, and it also colludes no collusion here. It also concludes the chapter. Okay, so thank you very much, and please try the exercise that accompanies this. It's really important that you get as much practice at this as possible.